Okay, so we've been talking about, again, the nerve cell, and we said the nerve cell is made up of electrical and chemical energy. The electrical energy would be the ions that are positive and those that are negative, and the exchange that occurs between positive and negative ions within the axon to cause a nerve impulse to occur. And then the electrical energy moves down through the ion, and when it gets to the end, we have chemical energy that is released. And it's released in the form of neurotransmitters. Some neurotransmitters are inhibitory, some are excitatory. But we know that we have electrical and chemical energy generated or distributed throughout the body for the control of various body functions. So that's the first concept. So the nervous system is a sensor. It receives information from the environment, and that could be information about touch. It could be information about temperature, pain, so forth and so on. It is an effector. It initiates all body movements. So that being said, that if I want to move my hand, the ability for me to do that starts at the level of the cerebrum, okay, in the motor area of the cerebrum, which is in the frontal lobe. It's an integrator. It combines information received from all sources and modality. So everything coming into the body has to be integrated and interpreted. Everything going out of the body has to be coordinated with everything coming into the body. So it is an integrator, and then it is a regulator. The human nervous system regulates your body temperature. We call this homeostasis. And so when somebody gets sick, your temperature goes up. But normally what happens is, if you're just functioning normally with nothing going on, no colds, no viruses, no bacteria, no damage to your system, then it helps to regulate the system so that your temperature remains the same. And it also helps with repair when things go wrong. And then, of course, it helps you and your body to be able to reach peak performance. So if I don't have a stroke, if I don't have any damage to the brain in any particular way, then I ought to be able to talk, I ought to be able to walk, I ought to be able to think, to remember, to do all those things normally, because the human nervous system regulates. It's a regulator. It maintains the regular body temperature, but it also maintains function. Okay? Any questions about those four things? So when you think about the human nervous system, I want you to think about it's a system that receives information from the outside. It initiates body movement, which makes it an effector. It integrates all sensory and motor information coming and going out of the body, and then it regulates the body. Okay? So those are four concepts that I want you to remember. Some of this is review because we talked about it in Chapter 1. The nervous system consists of the central nervous system, and it consists of the peripheral nervous system. So we already know that the central nervous system, when we think about that, we're talking about the brain and the spinal cord. The thing about the central nervous system is that it is very, very complex. It's responsible for the origination, planning, and transmission of conscious thought and deliberate actions. So I was thinking today about how am I going to solve the problem of getting home in time to teach by 6:50, and then what happens if I don't get home to teach by 6:50? Well, what I did was I called Angela. That's my central nervous system working. Now, why did I call Angela? Because I talked to Angela, and she was the first name I saw in my my text messages. So I called her, and the plan was We could either start at 7:30 or we could have class tomorrow. The only reason I was able to do that is because my central nervous system is responsible for me having conscious thought and deliberate action. So I deliberately called Angela. I deliberately came up with a plan because I knew that I needed to teach my class. Okay? So, without my central nervous system working appropriately, you probably would not have had this class tonight. I may have been sitting in traffic and not thinking about how to solve this problem. Maybe I couldn't solve the problem. Maybe my central nervous system no longer worked. So the brain is responsible for initiating, controlling, and regulating all sensory, motor, and cognitive functions that generate and regulate human behaviors. That's important. If I want to initiate a behavior, it's because the CNS is working. It helps to regulate all sensory, motor, and cognitive functions that are a part of the nervous system. So, very complex. So again, remember, the CNS is, in terms of those principles, it is designed based on a hierarchy. So you have the central nervous system and you have the spinal cord, but the spinal cord is basically reflexive. But as you move higher up in the central nervous system, it becomes more voluntary. The brainstem is involuntary. It controls swallowing and respiration and consciousness, and because if you go in a coma, usually it's a brainstem injury. When we get to the cerebrum, we're talking about deliberate planning, attention, memory, all those reasoning, executive functioning, inhibition of inappropriate behavior, talking, comprehending, calculating, doing calculations, feeling, feeling pain, feeling touch. All those things are higher order, okay? So sensory information that is collected from the peripheral body parts and the environment is transmitted to the brain via the spinal cord. Some sensory input is processed locally in the spinal cord and regulates peripheral reflexive motor activity. So when we talk about the CNS, if we're talking about information coming into the body, it must first come in through the peripheral nervous system, but then it has to go into the spinal cord, which is part of the central nervous system. If it is reflexive in nature, then it's going to go right back out through the peripheral nervous system, and some type of motor response is going to happen. So that's just like you're putting your hand on a hot stove and then you're removing it. That's not going to have to travel to the cerebrum to be interpreted. It's going to be reflexive at the level of the spinal cord. But if it's something that I really need interpreted, that is not going to be reflexive. It has to come in through the peripheral nervous system, go into the spinal cord, and then it's sent from the spinal cord into the brainstem, then into the internal capsule of the subcortical area of the brain, then to the cerebrum, where it's going to be interpreted in the parietal lobe. Okay? Any questions thus far about the central nervous system? Because what we're talking about is that the nervous system is made up of the central nervous system and the peripheral nervous system. But the central nervous system is, I guess, the type of behavior that occurs is hierarchical. So, you know, if it's just reflexive, it's at the level of the spinal cord. If it is involuntary, but life, you know, important for you to live, like breathing, swallowing, so forth and so on, is at the level of the brainstem at one level. And if it's voluntary, then it's at the level of the cerebrum. The CNS is protected by a bony shell. It is encased in the skull. The brain is encased in the skull. The spinal cord is protected by the vertebral column, which consists of a series of bones and cartilaginous washer-like structures. And those washer-like structures are important for buffering body movements, and they also help to bear weight. The CNS is encased in the meninges. The meninges are the covering of the brain. So you have the dura mater, the arachnoid, and the pia mater. Mater means mother. Okay? Those are the three layers from the outermost to the innermost. The dura mater is the meninge that is right below the skull. The arachnoid is the area between the dura mater and the pia mater, and the pia mater actually adheres to the surface of the brain. Okay, so from outer to inner, dura, arachnoid, pia mater. From inner to outer, pia mater, arachnoid, dura mater. Okay. Cerebrospinal fluid flows between the arachnoid and the pia mater. So that's important because it also acts as a buffer and as a chemical mediator for metabolic functions. The meninges provide the supporting framework for the central nervous system vessels that carry blood to and from the heart. Okay, so if a kid has meningitis, it means that the inflammation occurs to the whole brain. It occurs to all the meninges. Think of it as a cover or a cap for the brain. So inflammation of the meninges means that the problem, the infection, is across the whole brain. So think about that as well too. And most kids with meningitis, they really are in serious trouble. I have a friend whose son had meningitis, inflammation of the meninges, and he had learned to walk and talk. He could no longer walk. He couldn't talk anymore. He had to learn to sit up. He had to learn to crawl, walk, and talk. Okay? You had it in 10th grade? Wow. Lydia, talk to us. What were your symptoms? If you can you talk to us? Oh, not Lydia, Lindsay. You can't actually talk. Severe headaches that would not go away. How did they treat you? I'm sorry, Whitney, is there two different types of spinal and one in the brain? What do you mean? And antibiotics, okay. Yeah, there are. Okay. Wow. Your vision worsened? Good. Well, my friend's child was a baby. I mean, he was probably 3 or 4. He was 4. It was traumatic. Somebody in the daycare had meningitis, and I mean, it just he caught it, and I don't think they diagnosed it for a long time, and that became very problematic for him. But he's doing fine. He's a young man. He's probably about 28 now, so this was a long time ago. So remember that the meninges are there to provide support to the CNS, and from the outer to inner layer, because I do ask that as a test question, you have the dura mater, the arachnoid, and the pia mater. Okay? The peripheral nervous system consists of sensory and motor nerves that are connected to the spinal cord. So you have your spinal nerves, and then you have your brain stem. And if you look on page 36, you see a picture of the central nervous system in figure 2, which consists of the cerebrum and the spinal cord. And then if you look at figure 2.1b, you see the peripheral nervous system. And you see the spinal nerves coming off of the spinal cord, and you see the cranial nerves coming off of the brain stem. Okay? These nerves extend to organs, muscles, joints, blood vessels, and the skin surface. So information, when it comes into the body, it really comes in by way of some sensory stimulation to an organ, a muscle, a blood vessel, a joint, or skin surface. And then that information goes to those peripheral nerves. And the thing is again, if the information that comes in is something that causes a reflex to occur, then the information is not sent up through the spinal cord, through the brainstem, through the internal capsule to the cerebrum. It just goes right back out through the peripheral nerve to the skin or the joint or whatever. So, just to kind of give you a picture of what happens. The peripheral nervous system also consists of the somatic nervous system and the autonomic nervous system. And each of these systems consist of sensory or afferent and motor efferent fibers. The afferent fibers consist of nerves and cells that transmit, of course, sensory information to the CNS from receptors either in the skin, the muscles, or the visceral organs. If it is efferent, then information is motor in nature. And so it causes some type of motor response to occur in some type of visceral organ or gland or in a muscle or whatever. So when we think about the autonomic nervous system, and all this is on page 36, the autonomic nervous system consists of visceral organs, involuntary, or it's a vegetative system. And it regulates the activity of all of these organs that we see listed here: your heart, your lung, your stomach, your kidneys, your bladder, so forth and so on. With this being said, when you're really frightened or afraid, your heart starts to beat. Okay, that is motor in nature. I mean, it's movement. Okay, your stomach might start churning. You might have to go to the bathroom. You might urinate on yourself. So all that stuff is involuntary. All of a sudden, your involuntary system or vegetative system just goes into overdrive. Okay, so that's what I want you to think of when you think of the autonomic nervous system. It's involuntary, it's visceral, or it's a vegetative system. And it is made up of the sympathetic nervous system, which either expends energy as it activates visceral organs and glands in response to you've got to fight, or you got to run, or you have some kind of fear. Okay, and the sympathetic ganglia, which is a cluster of nerve cells, usually innervates many of these organs. So for me, I have a fear of heights, or sometimes you just get afraid because you know you're not going to make something on time. And then, like today, my sympathetic nervous system really wasn't in overdrive because I was trying to problem solve. But I was irritated because I was backed up in this traffic, and I could have stayed in my office. But I was able to control pretty much my emotions. But when I was trying to get to that bid whist party and going up the what did I tell you I went up? I can't think of the name of the thing. Oh my God. Anyway, I was so afraid. And so just, heart racing and hand sweating. And I mean, just wanting to run away or get out of the situation, but I had to stay as much in control as possible. So the sympathetic nervous system is part of the autonomic nervous system because it's visceral, it's involuntary, it's vegetative. And it just goes out of whack when something happens. I mean, you feel like you got to pee on yourself or something. The parasympathetic nervous system actually conserves energy, whereas the sympathetic nervous system expends energy. So the parasympathetic nervous system brings the visceral functions back to normal levels. So then the heart rate slows. Actually, I didn't get back to normal level, even though I got off of the grade. I was on what was I on? I can't even think of what it was. No, I can't think of it right now. I'm sorry. But the point is that I went up this elevation, and then there was this drop, and then I turned onto a side road where you had land on both sides, but I still didn't have any control. I was still afraid. And even when I turned into the neighborhood I was going into, houses were on both sides of the street, but the road was going up. It was elevating. It wasn't until I actually parked the car that I could calm myself down so that the parasympathetic nervous system actually began to bring me back to normal levels. Okay, so things to remember. Central nervous system consists of spinal cord and cerebrum. Autonomic nervous system consists of cranial nerves and spinal nerves. Autonomic nervous system, involuntary, vegetative. So made up of sympathetic nervous system, which expends energy, causes you to, those visceral organs to go into overload, so the eyes become really wide, heart rate rapid, hands sweaty, so forth and so on. Parasympathetic nervous system conserves energy and brings your visceral functions back to normal level. So the ANS is visceral and involuntary and vegetative. Okay? Now let's talk about the major primary divisions of the brain. You have three major vesicles. If you look on page 37 of your textbook and look at figure 2.2, you can see the three major vesicles. You have the prosencephalon. The prosencephalon, if you look at your book, they're showing you the development of the prosencephalon. We call the prosencephalon the forebrain, but the forebrain can be divided further into, it develops into the telencephalon and the diencephalon. So the telencephalon consists actually of the cerebral cortex. So if you look at the telencephalon in this picture, you'll see that you have a pictorial representation of what looks like the right hemisphere and the left hemisphere. But it's not only the cerebral cortex, it's also the deep structures that are beneath the cerebral cortex, which are the basal ganglia, the limbic system, and the lateral ventricles. Okay? The diencephalon is, you can only really see in a mid-sagittal cut, and it consists of the thalamus, the hypothalamus, and the third ventricle. So I'll show you this when I show you a picture in a few minutes. But the prosencephalon is the forebrain that develops into the telencephalon and the diencephalon. You must know these structures. So I need you to learn them, okay? Because you will be tested on this. You also have the mesencephalon. And the mesencephalon refers to the midbrain. Now the brainstem consists of the midbrain, the pons, and the medulla oblongata. The mesencephalon is the midbrain of the brainstem. Okay, so it consists of the midbrain structures and the cerebral aqueduct. Now, we talked about the lateral ventricles, the third ventricle. We're talking about a cerebral aqueduct. So in the lateral ventricles, or in the ventricles, we have an organ or a structure called the chloroid plexus. And the chloroid plexus produces cerebral spinal fluid. The cerebral spinal fluid flows through the lateral ventricles into the third ventricle by way of the foramen of Monroe. Foramen is just a hole, okay, the interventricular structure. And then we have, at the level of the midbrain or the mesencephalon, we have a structure called the cerebral aqueduct. Cerebral spinal fluid flows from the third ventricle into the fourth ventricle by way of the cerebral aqueduct. Okay, any questions thus far? So we're talking about the divisions of the brain, the three major vesicles. So the first vesicle is the prosencephalon. The second is the mesencephalon. The prosencephalon is the forebrain. The mesencephalon is the midbrain. And then the third vesicle is the rhombencephalon. The rhombencephalon is the hindbrain. So I need you to think forebrain, midbrain, hindbrain. The forebrain consists of the telencephalon and the diencephalon. The midbrain consists of the mesencephalon, which is the midbrain structures and the cerebral aqueduct. And then we have the rhombencephalon, which can be divided into the metencephalon, which is the pons, the cerebellum, and the fourth ventricle, and the myelencephalon, which is the medulla oblongata. Okay, so those divisions are figure 2.2, and they're showing you in figure A, 2.2a, the embryonic primary vesicles, which are the prosencephalon, forebrain, mesencephalon, midbrain, and rhombencephalon, hindbrain. And then they're showing you the major divisions of the brain. And what you see is the telencephalon consists of the cerebral cortex, so those two hemispheres, but also you have to remember that the telencephalon will also consist of the basal ganglia. It'll consist of the limbic system, and of course the lateral ventricles. Then we have the diencephalon, which consists of the thalamus and the hypothalamus and the third ventricle. We have the mesencephalon as another division, which consists of the mesencephalon, which is the midbrain, and the cerebral aqueduct. Then we have, in the rhombencephalon division of the hindbrain, we have the metencephalon, which is the pons and cerebellum, and the fourth ventricle, and then the myelencephalon, which is the medulla oblongata. You don't have any ventricle at that level. If you look at table 2.1, it gives you the embryonic brain vesicles, the major divisions of the brain, and the gross anatomic structures. Please make sure that you learn table 2.1. You will see it again. Okay? Any questions about those structures? Because we're getting ready now to get into the telencephalon. Okay? Now I know that this is what you have to learn, so hopefully you've already had an opportunity to read chapter 2. And then what I'm going to be doing is pointing out structures to you from here on out, because I believe my pictures are about to come up. So remember, we said the telencephalon consisted of the cerebral cortex. The cerebral cortex consists of the frontal lobe, the parietal lobe, the temporal lobe, and the occipital lobe. It also consists of the basal ganglia, which we talked a little bit about. The caudate nucleus, the putamen, and the globus pallus are part of the basal ganglia. And then the limbic system, the cingulate gyrus, hippocampus, amygdala, and I'll show you those. So what we're going to start talking about now is the telencephalon, and we're going to start talking about the cerebral cortex. So it weighs approximately 3 pounds. It's 12 to 14 grams. The cerebral cortex consists of 2 cerebral hemispheres, makes up the largest part of the brain. It's convoluted. It has a convoluted surface, and is composed of 3.5 millimeter thick layers of neurons. So the surface is composed of neurons, and it is the gray matter. The gray matter overlies the internal white matter in the basal ganglia. So the cerebral cortex is convoluted, and it does consist of neurons, layers of neurons. If it's gray matter, it's got to be the cell bodies. If it's white matters, it's the dendrites and the axons. Okay? So here is the cerebrum of the cerebral cortex. Okay. And, excuse me. Okay. So here, in blue, what I'm drawing are the convolutions. And this is a gyrus, or these raises are gyri. Okay? Can everybody see the blue drawing? Okay. Beautiful picture of the cerebral cortex. This is all gray matter. All of this covering, all of this is gray matter, which means in terms of a nerve cell, this is the cell, these are the cell bodies or whatever. Okay? All right. But when we remove the gray matter, you can see the white matter. So the white matter are the dendrites and the axons. All right? Okay, so this is why I like this these slides, because they're going to show you, I'm going to try to remove structures and let you see what's under those structures. Okay, so we looked at the gray matter, and now we can see the white matter. All right, and here is the white matter. It's just under the gray matter. So these are fibers, and if these are fibers, if they're white matter and they're axons, the corona radiata would be the crown. Okay? The crown, all this white matter that projects down deeper and goes into the spinal cord. Okay, so that would be, those are projection fibers. Here, when you remove the whole cerebrum, you can see all the white matter. Okay, so let's go back. All right. Now, so we already talked about the convolutions. Really the ridges. That's what I should call it, because I said convolutions, but it's not. The convolutions are the sulcus. And so if we go back and look at this, these raises that we see, let's go back here. These are raises or gyri. But if we want to think of convolutions, those things right there in green, those are your sulcus. That's a sulcus or sulci if we're looking at the indentations. Okay, so the raises are gyrus, and the indentations are sulcus or sulci if we're talking about more than one. Okay. All right, so let's see. Cortical ridges called gyri, the grooves are fissures. Well, I guess convolutions, what's the right word then? Anyway, convolutions allow for the accommodation of a larger cellular volume within a limited cranial space. Because you got to think about the fact that all of this brain, this soft matter, is encased by bones. It's a bony skull. So that's why, like when swelling occurs in the brain, or some type of swelling, that you have to remove the skull because the brain has nowhere to go. Okay? The cerebral hemispheres are separated along the midline by the longitudinal fissure, and another name for this is called the interhemispheric fissure. Okay, so here is the longitudinal fissure, and a fissure is just a deep hole. Now, you can also see where the green is that I did not draw, so I'm just going to point to it by using, I guess, blue or whatever. Okay, or black. This area here that I have colored in green, but now that I'm coloring in blue or black, that is the corpus callosum, and those are this is the commissural fiber that connects the right side of the brain to the left side of the brain. Okay? Any questions thus far about structure? Here you can see with the cerebrum removed, or the gray matter removed, we're looking at axons and dendrites. This is the white matter. But isn't this a beautiful picture of those commissural fibers that connect the left side of the brain to the right side of the brain. So the left hemisphere to the right hemisphere. Okay? Any questions thus far? So we talked about the structures of the central nervous system, of the peripheral nervous system. We've talked about the three vesicles of the brain during the developmental period and the major divisions of the brain, and now we're talking about structures of the telencephalon. So what we know is that the cerebral hemispheres, they look alike. They mirror each other in image. And one side of the body is controlled by a particular hemisphere. So the right hemisphere controls the left side of the body. The left hemisphere controls the right side of the body. So this is one of those principles that we talked about in the Chapter 1 when we were talking about the principle of laterality of brain organization. Okay? And so we talked about contralateral sensory motor control. And this is what we're talking about. So if there's damage to the right hemisphere, then I should see some weakness to the left side of my body. If there's damage to the left hemisphere, I should see weakness to the right side of my body. And so that's how when we look at someone who's had a stroke, well, I know whether it's a left hemisphere stroke or a right hemisphere stroke by just simply looking at what side of the body is affected. Okay. We also know that both hemispheres contain centers that are important for processing sensory information and motor information. But we know that the hemispheres are specialized. So this also, when we talk about specialization, we're talking about unilateral functional differences, which is part of laterality of brain organization. The left hemisphere is specialized for language and speech and verbal memory. The right hemisphere is the emotional side of the brain. It's the musical side. It's the visual and spatial side. It's also important for processing pragmatic skills. So when somebody has damage to the left hemisphere, they may not be able to speak or understand or read or write, or they may not be able to repeat, or their language may not be very fluent. But if there's a problem with the right hemisphere, then they're going to be able to talk. Their language will be fluent, but they may not understand metaphor, or they may take everything literally. So higher order language skills are affected when there's right hemisphere damage. There's also problems with prosody, rhythm, all those kinds of things, and spatial concept and time. So what we know is that those cerebral hemispheres are specialized. Again, part of the brain laterality principle. Okay. Now, the cerebral hemispheres consist of 5 lobes, 4 of which are named after the overlying bones of the skull. So we have the frontal lobe, the parietal lobe, the occipital lobe, and the temporal lobe. And the other lobe that you don't think about is called the insula. And the insula is really a small little island that's very deep below the lateral sulcus, and it's overlapped by the frontal, parietal, and temporal lobes. And so remember we talked about that term opercular? Opercular means that there are areas that meet at a particular margin. And I said if we pull the operculars back, then what you can see is the insula. So we're going to show you the insula after we look at the lobes of the brain. So here, this is the frontal skull, or frontal bone, the parietal bone, the temporal bone, and then we have the occipital bone here. And they overlie the frontal lobe, the parietal lobe, the temporal lobe, and the occipital lobe. So you guys learn these, you learn these bones when you took anatomy and physiology. You also learned about the zygomatic process, the mandible, the maxillary, the I can't say it, sphenoid bone, so forth and so on. Okay. Okay. So here in red, frontal, in blue, parietal, yellow, temporal, and green, occipital lobes. Okay. And you can see that these lobes have many gyri and many sulci, sulci. Okay? So we have to learn the names of those sulcus, and that's what we're getting ready to do. Okay. Any questions thus far? Anybody have any questions? Okay. So this part should be kind of like just a review to help you learn the names. And so you can see this is just another representation of the frontal, parietal, occipital, and temporal. But you also have here the cerebellum, and then you have the brain stem down here. And what you can see is the pons here, and you can see the medulla oblongata here. Okay? And I think I have another picture, and here's the other picture. Now, remember we said we had 5 lobes. So here is the frontal lobe. Here is parietal. Here is temporal. And look, we have pulled back or removed areas of the temporal, parietal, and frontal lobes so that you can see the insula. This is the 5th lobe here. The occipital lobe would sit back here, and you cannot see it in this picture. So there are 5 lobes, not 4, but 1 lobe is hidden. Okay? All right. So that's a beautiful picture of the insula. Now what I also want you to see is we talked about these fibers. And so let's go back here. We talked about white matter. This is gray matter here. So I'll just put the G for gray. But where you see the green, that's white matter. But look at these projection fibers that I'm coloring blue. They're in green. This is the corona radiata. This is the corona radiata, or the what? Radiant crown. And look what it is surrounding or going in between. Here sits a beautiful picture of the insula. There is the insula. Okay? Here's another picture of it. Clearly you can see the corona radiata, our projection fiber. And look at this beautiful picture of the insula. And Heschel's gyrus is also over here. Okay? And that's important for hearing, just knowing that you can hear, not understanding what it is that you can hear, but knowing that you can hear. Hold on. Okay. Anybody have any questions thus far? Beautiful picture of the cerebellum. And the only thing that you can see down here is medulla oblongata. You can't see the pons, you can't see the midbrain. Okay, but I'm coloring the medulla oblongata blue. Heschel's gyrus sits over on the far end. So let me change the color of it. Okay. All right. So, I was trying to color it yellow. Yeah. It'll be over here. No, it's just, some people just call it the medulla. And if you want the full name, it's the medulla oblongata. It just means the long area of the brain. Oblong is long in shape. Okay. The corona radiata is a projection fiber because it projects from the cerebral cortex down, and those fibers run down and then into the internal capsule, and they would run through the brain, the brainstem and the spinal cord. So they project from the top of the brain down through the brainstem. Okay. Any other questions? Okay. So now we're going to learn the names of the sulci, or sulci, but sulci, I believe, is the plural. So you have three major sulci that are present on the dorsolateral surface of the brain. You have the central central sulcus, which is the fissure of Rolando. And it begins at the top of the brain, midway between front and back, and extends in a downward and rostral towards the front area. It's 2 centimeters deep, so I'll just kind of show it to you in a minute. So one of the fissures that you're going to learn is the fissure of Rolando, which is also called the central sulcus. Then we have the Sylvian fissure or the fissure of Sylvius, and this is the lateral fissure that separates really the parietal lobe from the temporal lobe and part of the frontal lobe from the temporal lobe as well. Okay, so it's going to begin rostrally, meaning towards the front, below the frontal pole, and extend posteriorly toward the inferior parietal lobe. It separates the frontal and temporal lobes anteriorly, and posteriorly it extends partially between the parietal and temporal lobes. Okay, so when we look at this, here we have the fissure of Rolando. I'm going to draw it. Okay, I'm sorry, I messed up in terms of, but where you see the deep division, then what we have is this fissure separates what? The frontal lobe from the parietal lobe. Okay, but then we have the, let's do this. We have the Sylvian fissure, or the fissure of Sylvius, or the lateral fissure, which I'm drawing in blue. It separates the frontal lobe from the temporal lobe. Okay? All right. But this fissure also separates the temporal lobe from the parietal lobe. Okay? Everybody got it? So you have to know the names of those fissures, and you have to know all of the names of the fissures. So I'm getting ready to teach you that. Okay? So here, where you see this green that I'm drawing blue on, that is the Rolando fissure, or the fissure of Rolando. Okay? Any questions about that? Now, the nice thing that you need to know is that this is the central fissure, or the fissure of Rolando, but it separates the primary motor cortex, which is here, primary motor cortex, from the primary sensory cortex. Okay? So that's important. And in terms of Brodmann's number, this is Brodmann's area 4. The primary motor cortex is where the homunculus hangs upside down, and it is responsible for all movement of all body parts. This area, I believe, is area 2, 1, and 3. 3, 1, and 2. 3, 1, and 2, Brodmann's areas. And the homunculus hangs upside down on that area as well, but it's responsible for all sensory information coming into the body. Okay, so that's where the information is received. Now, it's not where it's interpreted, but it is where it is received. But what divides the primary sensory cortex from the primary motor cortex? The fissure of Rolando, or the central sulcus. Okay? All right. Now, if you look where the green is, and here's the start of the green, and I'll just let you follow it. This is the, fissure of Sylvius, or the lateral fissure. Okay, so you have a lateral fissure and you have a central sulcus. Lateral sulcus, or fissure, and a central sulcus. So lateral fissures, another name for the lateral fissure is the fissure of Sylvius, or the Sylvian fissure. Another name for the central sulcus is the fissure of Rolando. Okay. We also have a third major sulcus in the telencephalon that divides the occipital lobe from the parietal lobe, and it is called the parietal occipital sulcus. Okay? But the thing is on the lateral surface of the brain, you cannot see it, so we have to look mid-sagittally to see it. So where you see the green, here, there you go. That is the parietal occipital sulcus. It divides the parietal lobe, and this is a sagittal viewpoint from the occipital lobe. Okay, here's the frontal lobe here, and you can only see the bottom of the temporal lobe here. Okay. Now remember we said there was a limbic system. So this green area here is called the cingulate gyrus, and this is part of the limbic system. But here is the diencephalon. Here's the thalamus, and here is the hypothalamus. This is diencephalon. I was trying to draw H. I didn't do a good job drawing an H. Thalamus, hypothalamus, diencephalon. Okay? But this cerebral cortex that you're looking at is telencephalon. What did you say? This was mid-sagittal view or medial? No, it is the mid-sagittal view. Mid-sagittal means that you cut the brain in half. So you're looking at the left side of the brain. So where you have that longitudinal fissure, we just separated the brain. And that being said, here's the corpus callosum. Those are the fibers of the corpus callosum, or the commissural fibers. Okay? All right. Here's the brain with all of the names of the structures. And if you will look on page 40, you will see in figure 2.4a the central sulcus, and you will see that it divides the motor cortex, or the primary motor cortex, from the primary sensory cortex. The central sulcus divides the frontal lobe from the parietal lobe. The lateral fissure, or the fissure of Sylvius, or the Sylvian fissure, divides the frontal lobe from the temporal lobe, and actually it extends up and divides the parietal lobe from the temporal lobe as well. If you look, still looking at figure 2.4a, you will see the parietal lobe in dark pink being divided from the occipital lobe, which is in light pink, by the parietal occipital sulcus. But on that lateral viewpoint, it is imaginary. So in this figure that you're looking at in front of you, but not in the textbook, but in Blackboard Collaborate, here I'm going to draw what would be considered the parietal occipital sulcus, because you can't see it. It's imaginary from the lateral viewpoint, but from the mid-sagittal viewpoint, it's very, very clearly demarcated. So here it is. It actually curves down a little bit to this notch. That would be the parietal occipital sulcus. Now, let's look at the sulcus and the gyrus. First, we're going to look at the frontal lobe. So here is frontal lobe here. I'll put the F out here, and I'll just point. Okay. So what you have is the central sulcus here. Okay. In front of the central sulcus you have, they're calling it the anterior central gyrus, but you need to know it as the primary motor cortex, or the precentral gyrus. This is the precentral gyrus. So where you see the word anterior, you can change that to pre, or whatever. Okay? We're only looking at the frontal lobe. You also see here that in the frontal lobe you have 3 gyrus. Okay? You have the superior frontal gyrus. So this is the most outermost gyrus. Okay, and it extends all the way down here. All right. Then what we have is we have the middle frontal gyrus, and it's all of this. And then what we have is the inferior frontal gyrus. So you have three gyri. Okay? And I'm trying to just make them different colors so that you will not have any problems with them. Okay? Here's the inferior frontal gyrus. As part of the inferior frontal gyrus, you have Broca's area, and Broca's area is here where we see pars triangularis. Okay, so this is area 44. All right. Now, let's look at the sulcus, or the sulci. And I'm going to do it this way. Okay. You have here, it's hard to see. I'm trying to draw the sulcus, but they're in black. That's the superior frontal sulcus that divides the middle frontal gyrus from the superior frontal gyrus. And then you have the inferior frontal sulcus that divides the middle frontal gyrus from the inferior frontal gyrus. Okay? Any questions about that? So you have three gyri in the frontal lobe, along with the precentral gyrus, which is the primary motor cortex. Jenna, do you have a question? And if you have a question, you can raise your hand and you can talk.
Yes, ma'am. What's the sulcus you said? I can't read it. What's the sulcus you said that divides the middle frontal gyrus and the inferior?
It's the inferior frontal sulcus. So the inferior frontal sulcus divides the middle frontal gyrus from the inferior frontal gyrus. And then you have the superior frontal gyrus. It is divided from the middle frontal gyrus by the superior frontal sulcus. Oh, that's okay. All right. Jenna, you are funny. She says she's blind as that. Okay, so guys, if you can't see the structure names, let me know. But we'll see this. We'll see this structure again. Okay, so that's the frontal lobe. If we look at the parietal lobe, then we have, and I'll show you this again, but I'm just pointing this out. The interesting to note about the parietal lobe is you have the, let me just get a different color. Okay, here's the post-central gyrus here that I'm coloring red, or the primary somatosensory area or cortex. Okay? This is the post-central gyrus, or the primary somatosensory cortex. But you also, so this will be areas 3, 1, 2, Brodmann's area. But let's look at the superior parietal lobule, because you don't have a middle parietal gyrus. You only have a superior parietal lobule, and you have an inferior parietal lobule. Okay, so let me color that. I guess we can go here, something. Okay, so here is the superior parietal lobule. But this is Brodmann's areas 5 and 7, and this is where you interpret what it is you're feeling or what's causing the pain. Like, for example, when information on feeling comes into the body, it comes into the parietal lobe. But it comes into the parietal lobe at the post-central gyrus. The post-central gyrus area just tells you that you feel something, but it doesn't tell you what it is you're feeling. That information is sent from the post-central gyrus into the superior parietal lobule, where what it is that you're feeling is actually interpreted. So it could be, I'm feeling a hot cloth on my skin. I know what it is that I'm feeling because it's interpreted in the area where the superior parietal lobule is. So that's like an association area. What I also want you to look to see is that you don't have, let me do this. You don't have a middle parietal lobule, but you do have an inferior parietal lobule. And this is it. If I can draw it. It didn't change in color, but that's the inferior parietal lobule. Okay, and it's divided from the superior parietal lobule by the intraparietal sulcus. Intraparietal sulcus. Okay? Now, in the inferior parietal lobule, you have, let's find, I guess we'll do it like this. Okay. You have the supramarginal gyrus, which is here. It goes around the end of the lateral sulcus, the fissure of Sylvius. This is responsible for writing. And then look at the end of the superior temporal sulcus, but still part of the parietal lobe, you have the angular gyrus, which is important for reading. So the supramarginal gyrus and the angular gyrus, they're both responsible for reading and writing. Okay? So let me just color that for you. Okay. So here's the angular gyrus here. Well, that's so similar. Let me change it to another color. Okay. Here's the angular gyrus here. If I can make it color. Come on, color. Okay, there you go. And that's at the end of this superior temporal sulcus. Okay, so reading and writing, supramarginal angular gyrus. If we look at Brodmann's number, it's going to be areas 39 and areas 40. Okay? But what we're going to do is we'll look at Brodmann's numbers in a few minutes before it's over. But 39 is going to be the angular gyrus, and 40 will be the supramarginal gyrus. Okay? Now, if we look at the temporal lobe, then you have a superior temporal gyrus, a middle temporal gyrus, and an inferior temporal gyrus. So you have that going on again. Okay. So if we were to draw this, not draw it, but here is the superior temporal gyrus. that's separated from the middle temporal gyrus by the superior temporal sulcus. So all of these gyrus, all of them have a name, and you got to learn the names. Okay? Here is the middle gyrus here. And then the middle gyrus is separated from the inferior temporal gyrus by the middle temporal sulcus or the inferior temporal sulcus. Depends on whose book you're looking at. And so, here it is. So each of these gyrus, they have a name, okay? And that's what I'm pointing out to you in this picture. Yes, you will be asked to know, you'll be asked to know the functions of the lobes, but not of the gyrus, but you'll be asked to identify the gyrus, their names and the names of the sulci. Okay? All right. Now, this is a mid-sagittal view of the brain. So we have lots of structures in the mid-sagittal viewpoint. And what I want to point out to you is when we look at, yeah, certainly you will, Nikki, I will. I'll put one in for you to draw on. Okay. In this mid-sagittal view, I want to point out frontal lobe here in blue. Okay, all of this is frontal lobe. Okay. And here is parietal lobe here in this orange, and then this red is occipital lobe, but you cannot see the temporal lobe in this viewpoint. It's really down here below the brainstem, okay? So this is telencephalon here. This is diencephalon here. Here is mesencephalon, where the midbrain is. The pons is metencephalon, M-E. I know it's hard to see this. And the medulla is myelencephalon, M-Y. So those are the divisions of the brain. And we'll look at these structures a little bit later, because here is corpus callosum, which is a commistral fiber. And right there, underneath it, is septum pellucidum, which is a covering that divides one side of the lateral ventricle from the other side. Okay. We'll get to those in a minute. Okay, so we just looked at the frontal lobe, and we said that it is rostral, or in front of the central sulcus. It's the largest lobe, occupies 1/3 of the hemisphere, and it has 4 gyri. You have the precentral gyrus, which I showed you, and then you have the 3 horizontal gyri, which is the superior, the middle, and inferior frontal gyri. Okay? And there you go. So in the green, anytime you see green, that points out the structure that I'm naming. Here is the precentral gyrus. All right? This would be in the pink. This would be the superior gyrus. In the brown, the middle gyrus. And in the blue, in purple, the aqua purple, this is the inferior gyrus, but this is also Broca's area. And those are also those operculars we talked about. Opercula triangularis, orbitalis, and I can't think of the other one. Triangularis, orbitalis, and what's the other one, guys? I can't remember. I can't say it right now. Well, I'll pull it up because I just went blank. Oh, pars opercularis. Yeah, pars opercularis, pars triangularis, and orbitalis. Okay. So you're also looking at in green here outlined, this is the primary motor cortex. So the precentral gyrus is the same as the primary motor cortex, and the homunculus hangs upside down on it. Okay? The frontal lobe has a prefrontal cortex, and this is Brodmann's areas 10 through 12. This is considered as the biological correlate to human intelligence and contributes to reasoning, abstract thinking, decision-making, planning, self-monitoring behaviors, and pragmatic behaviors. So here, this area now that's outlined in green, this is the prefrontal cortex. This is also called the language or the cognitive, pre-language or cognitive cortex, because all of your cognitive functions, so it's areas 9, 10 through 12. Now I want you to look at page 41 in your textbook. And just look at the frontal lobe area. Let me know when you have page 41, because I want to point out what I want you to find on 41. Okay. All right. So look at, first find the central sulcus, the sulcus of Rolando, the fissure of Rolando. And then you'll see the precentral gyrus in front of it. And then you'll see the superior frontal gyrus, the middle gyrus, and the inferior frontal gyrus. Okay, now, when you look at that, in the very frontal area, if you turn on page 42, remember that we said this constitutes areas 9 through, I think, 12, okay? So look at Brodmann's areas. Look at the Brodmann's areas. Okay, so if we go back, what we said, the area for reasoning, areas 10 through 12, you can't really see 12 on figure 2.6b, but you really, it's areas, Brodmann's areas 9 through 12, okay? And that's what we consider the frontal part of the prefrontal lobe of the brain, okay? And all of those things, reasoning, self-monitoring, decision-making, so forth and so on, occur in that area of the brain, which is this area in green that I have highlighted in green. Okay, so if you get in a car accident or if you're playing sports, and particularly football, you can see then why the person would have some problems with abstract thinking and reasoning and so forth. Why? Because that's the cognitive or language area of the brain, okay? And when you get in a car accident, if you're thrown forward, the first thing you hit is that area of the brain. If you're doing contact sports in football, you have one helmet hitting the other helmet, and that's the area of the brain that's being damaged. So that's why you say, boy, the areas 9 through 12, if you look at area 11 on figure 2.6, that area is the area, and 12 like goes further under. If you have damage in that area, you have problems with inhibition. So that you can't inhibit your behavior. And so you'll do things that you would never do. You'll say things that you would never say, okay? But I also want you to look at area 4. Area 4 is the primary motor cortex or the precentral gyrus, and this is in the frontal lobe. So this is where that homunculus hangs upside down. And if you look at figure 2.6a, you see a man hanging upside down on the precentral gyrus or the primary motor cortex. You can see that the mouth is located here, lower on the primary motor cortex or Brodmann's area 4. Okay, so But this area here is Broca's area, where language is represented. So if that lesion extends on into the lower part of the precentral gyrus, the person is going to have difficulty talking as well as using language. Okay. Any questions thus far? If we look at the sagittal view, we will see this is the frontal lobe in the pink. This is the parietal lobe here. And this is the occipital lobe. And the temporal lobe is really down here. Okay? Now, what you're going to see from this viewpoint is what we call a paracentral lobule. So that's this green area here. It is surrounding this central sulcus, or this is the fissure of Rolando. So that's the Rolando fissure. Okay, and the paracentral lobule means by the central lobe. That's what it means. Okay? All right. Any questions thus far? Here's an example also of the prefrontal cortex, areas 10, or really 9, through, let's say 10, 11, down here more orbital, and 12. Okay, so that's the prefrontal cortex as well. All right. Here is the primary, this is area 4. This is the primary motor cortex. And this is area 3, 1, and 2, which is the primary sensory cortex, or the postcentral gyrus. So you got to learn all these names. Okay? Now, you have a motor association area. If you look on page, again, 42 at figure B, you will see that the premotor area is area, the precentral gyrus is area 4. But if you look at the premotor cortex, then that is going to be area 6 and areas 8, 6 and 8. Okay? So you got to learn those areas. All right. So the motor association area is the premotor cortex, and these are areas 6 and 8. This is area 4. Okay, and then this is the premotor cortex, areas 9, 10. I messed up drawing it. 11 on down, and then 12 on around over here. Okay, and this is a sagittal view, so you can see that motor association area extends into the longitudinal fissure. Now, so first convolution of the frontal lobe is the superior gyrus. So convolution is gyrus. I was confused, but instead it was, then it wasn't, but it is. The second convolution is the middle frontal gyrus, and the third convolution is the inferior frontal gyrus. And so here is the superior frontal gyrus here, outlined. Okay. Then what we have is the superior frontal sulcus, which you see in the green here. Okay, that's the sulcus. So I showed you this already. Then what you have is the middle frontal gyrus here in the green. Then the inferior Frontal sulcus here in the green. And then what we have next is the pars opercularis. Opercularis means margin of a cerebral convolution. It serves as a cover. You have the pars triangularis and the pars orbitalis. The opercular and triangular portions of the inferior frontal gyrus in the dominant hemisphere constitutes the anterior language cortex, or Broca's area. And this is Brodmann's area 44. So let's look at it. Okay. So here in the green, this is pars opercularis in the green right here. Pars opercularis. Any questions about that? Okay. All of this is part of the inferior frontal lobe. Here is pars triangularis. Pars triangularis. Okay. And here is pars orbitalis. All right. Now, then you have also the anterior orbital gyrus, which is in this green area right here. Anterior orbital gyrus. You have the middle orbital gyrus, which is here. And then you have the lateral orbital gyrus, which is here. And this brown area here is pars orbitalis. The purple area is pars triangularis. And this aqua area is pars, I can't remember. Oh, pars opercularis. So pars opercularis, aqua, pars triangularis, purple area, the brown area, pars orbitalis, or it has to do with the orbit. And this area here constitutes Broca's area. Okay, so Broca's area is Brodmann 44. It's in front of the primary motor cortex, which is Brodmann area 4, and that contribute to the primary motor cortex that Broca's area is in front of, is where the face is, and it contributes to and controls the jaw, the lip, the tongue, the vocal fold movements. So pathology in the frontal lobe can result in a loss of speech, language, impulsivity, apathy, confusion, and problems in regulating behavior. Because when we talk about the orbitalis or orbital area of the prefrontal lobe, that's where you have the control to inhibit inappropriate behavior. And so when you become very impulsive, you're impulsive because there is some problem with that area, that orbital area. So impulsivity, saying things that are inappropriate occur when there's damage to that area. So here's the inferior frontal gyrus where you see it colored. And then here's Broca's area. So Broca's area consists of triangularis, pars triangularis, okay, all of this. Okay. And pars opercularis, which is here. But orbitalis is not a part of it. This is Broca's area. This is area 44. Okay. And here's the frontal lobe again, and you can see them pointing out structures of the frontal lobe, a precentral sulcus, superior frontal gyrus, middle frontal gyrus, inferior frontal gyrus. That consists of these three things: opercularis, triangularis, orbitalis. And here is the orbital gyrus, where we have problems when with inhibition of inappropriate behavior when there's damage there. Does anybody have any questions about the frontal lobe? Because we're getting ready to go on to the parietal lobe. So if you look on, again, page 42, you see all the Brodmann's numbers, and you need to know those numbers. Okay? Anybody have any questions? Okay, if everybody's good, then what we're learning is the lateral structure of the brain right now, and then we'll go on to different viewpoints of the brain. All right, so we're still in telencephalon, because remember the telencephalon and the diencephalon are part of the prosencephalon. So the parietal lobe is between the frontal and occipital lobes, and it is above the temporal lobe. And the central sulcus marks the anterior boundary of the parietal lobe. So the central sulcus, or the fissure of Rolando, divides the frontal lobe from the parietal lobe. And what we have is right directly behind the central sulcus, we have the post-central gyrus, the primary somatosensory area. Okay? Remember I said that the parietal occipital sulcus is imaginary on the lateral view because you can't really see it, but it extends from the preoccipital, it extends to the preoccipital notch, and it helps to mark the posterior boundary of the parietal lobe. So it begins at the top of the back of the parietal lobe, and then it extends to the preoccipital notch, not march, but notch. Okay. The parietal lobe is primarily concerned with perception of somatic sensation, and interpretation and elaboration of sensory sensation. So in other words, I know something is touching me. I know that I'm hot. I know that I'm cold. I know that I feel pain. So all of that's interpreted in the parietal lobe. It's felt in the parietal lobe on the postcentral gyrus, the primary somatosensory cortex. But then that information is sent from areas 3, 1, and 2, which we talked about. And if you're looking at figure 26B on page 42, you see areas 3, 1, and 2 as the primary sensory cortex of the post-sensory gyrus. So the fact that something is touching me, or I'm hot, or I'm cold, that's interpreted based on, you know, whether I'm feeling something on my arm, my legs, but it's interpreted as just having some type of sensation in areas 3, 1, and 2. But in order to figure out what that sensation is, the information has to be sent from 3, 1, and 2 to areas 5 and 7. In areas 5 and 7, it allows me to say, oh man, that's so cold. But what's cold, what you touch me with that's so cold is ice. So I know it's ice because that information is interpreted in areas 5 and 7, which are the association areas. Okay? So the primary area is where you actually feel the sensation, but the interpretation is done in the association area, which is area 5 and 7. All right. So we've already looked at the post-central gyrus and Brodmann's areas 1, 3, and 2. But the sensation is elaborated, or the awareness of the sensation is elaborated in Brodmann's areas 5 and 7. Okay. So here's the post-central gyrus in this green. And these are areas 3, 1. 1 is in the middle and 2 is on the outside. So you have to look at 3, 1, and 2 in the picture. That's the post-central gyrus. And then what you have you have the primary somatosensory area, so that's also areas 3, 1, and 2 are the post-central gyrus. It's outlined in green. Okay. Then, what divides the post-central gyrus from the somatosensory association areas, areas 5 and 7, and the superior parietal lobule from the inferior parietal lobule is the post-central sulcus. Okay, and that's in green. That's what you see here. And of course, if you do the sagittal viewpoint, here is the same thing. The post-central gyrus, or the primary somatosensory area from a sagittal viewpoint. Okay. Now, I also wanted to point out here, because the face is represented at the bottom of the post-central gyrus as well as at the bottom of the pre-central gyrus, then where you see this green down here, this is the primary gustatory cortex. And that's like for taste, because if you look at the homunculus on page figure 2.6a, you see that the mouth is located down at the bottom of both the primary motor strip and the primary somatosensory strip, or at the area of the lowest part of the precentral gyrus and the postcentral gyrus. Any questions about that? Okay. So, the primary association areas here in green. And then we also have the supramarginal gyrus and the angular gyrus, and those gyruses are important for reading, writing, and calculating. So, let's look at them. Here, as outlined, at the end of the lateral fissure, and here's the end of the lateral fissure, or the fissure of Rolando, we have this brown area. This is the supramarginal gyrus, or Brodmann's area 40, responsible again for reading, writing, calculation. Probably more writing here, reading angular gyrus more. Then this is Brodmann's area 39. And this is the angular gyrus. Supramarginal gyrus is area 40. But you can see that the angular gyrus surrounds the superior temporal sulcus, which divides the superior temporal lobe from the middle temporal lobe. Okay. Now, parietal lobe is also divided into the superior and inferior parietal lobes by the intraparietal sulcus. The parietal lobe is important for perceptual sensation, spatial orientation, cognition, memory, cross-modality integration, and a lot more. So when we look up here in this area, this is the superior parietal lobule. This is, well, I'll show you the intraparietal sulcus here. And then right below it is the inferior parietal lobule in green. Here is the supramarginal gyrus. Here is the angular gyrus. Okay, this area up here is areas 5 and 7. This is area 3, 1, and 2. Okay, and so hopefully that kind of helps. This is area 40. This is area 39. So learn the Brodmann's areas. As we talk about these different divisions of the brain, then of course we're also not just talking about names, but we're talking about Brodmann's areas. Okay. Lesions in the parietal lobe can result in contralateral sensory loss, problems with perceptual disorders of construction, so it would be hard for you to build, to draw, or to put things together. Disorders of spatial orientation and body schema. So I might not know where I am in terms of space, and I might not even recognize if it's a right hemisphere parietal lobe problem, that my body part actually belongs to me. I might say, well, that's not my arm. It doesn't belong to me. I might not be able to move my arm, but I won't recognize it as being my arm either. I'll have some memory deficits. I may have some hemi-attentional neglect or left side neglect, where it's not that I can't see what I'm looking at, but it's that I neglect whatever I'm looking at on that side. Okay? Oh, okay, yeah. When we look at hearing and we look at the insular area of hearing, then hearing is going to be 41. And it may extend to 42 too, because Heschel's gyrus is 41 and 42. And Heschel's gyrus is the primary auditory cortex, so it's both of them. So, does that answer? Now 40 is the supramarginal gyrus, and that's responsible for your reading and writing and calculation. But the angular gyrus is also responsible for that too, and so the angular gyrus is 39. So 39 is the angular gyrus, 40 is the supramarginal gyrus, 41 and 42 are the gyri of Heschel, and they are responsible for, it's the primary auditory cortex. Okay. Alrighty. Any other questions? Everybody good thus far? Okay, so we're talking about things, everything at the same time. We're kind of talking about where the structures are and what the function is, and we're talking about, and we're moving on, okay? Alright. So, lesions in the angular gyrus are Brodmann's area 39, and the supramarginal gyrus, which is Brodmann area 40, or both of those are located in the inferior parietal lobule of the dominant hemisphere. This will result in alexia. Alexia means a disorder of reading, so the person cannot read. Agraphia is a disorder of writing. And acalculia, is a disorder of calculation. Okay. So now the occipital lobe is only a small portion that's going to lie on the lateral surface. It's more fully developed along the medial surface of the hemisphere. It's going to contain the primary and secondary visual cortex. The primary visual cortex, where information comes in and you see something, is area 17, but where it's interpreted are in areas 18 and 19. Its anterior boundary is marked by an imaginary line extending from the ramus of the parietal occipital sulcus to the pre-occipital notch. And so that's the parietal occipital sulcus. But what you can see here is the superior parietal gyrus back here. It's hard that, not a lot of it is seen, like I said, in the lateral viewpoint. Okay? So there is the superior occipital parietal gyrus. And if you look at that on page 42B, that's area 18, and then you can also see area 19. Okay? So 18 here, and these are association areas, and 19 here. Okay. But if we were to look at and then there's a lateral occipital sulcus here. Okay. That divides the superior sulcus from the inferior. Okay. So there's the inferior occipital sulcus. So the superior from the lateral viewpoint would be Brodmann's area 18. The inferior from the lateral viewpoint is going to be Brodmann's area 19. And they are separated by the lateral occipital sulcus there. Okay, so now, if we look at the sagittal viewpoint, then in the green here is the primary visual cortex, and that's Brodmann's area 17. Okay? That would be Brodmann's area 17. And let me look to see. Yeah. If you look on page 21, figure 18A and 18B, you see all of your Brodmann's areas. Okay, so the visual association area is here, and this is areas 18 and 19 is here as well. Area 18 extends above here as well. Okay. Oh, I don't know why I'm doing that's the frontal lobe. I'm sorry, guys. Forget about that. I know that looks stupid. I'm tired. Here you go. The visual association area from the lateral viewpoint. I thought I was looking sagittal. I wasn't paying attention. So visual association area, area 18 and areas 19. Then we'll see it in the sagittal viewpoint. And now, here you go. Visual association areas here, 18 and 19. Okay? And then the occipital lobe from the sagittal point also has structures called the cuneus. You have the precuneus, which is here, and then you have the cuneus, which is this yellow which is there. So there, and here is the parietal occipital sulcus here, and then what you have is the cuneus here. Precuneus here, parietal occipital sulcus, P-O-S, and then you have the cuneus here, C for cuneus. All right. And we also have a fissure that divides the cuneus from parts, the occipital temporal gyrus here. So this is the calcarine sulcus here. Here is the lingual gyrus here. And here is the occipital, the medial occipital temporal gyrus here. And then last but not least, we have the temporal lobe. And we're going to do 2 more slides, I believe. And then we'll stop. No, we'll stop because it's after 9:30 now. 9:33. So we'll finish with the temporal lobe, and then we'll go into some deep structures, and we'll look more at function the next time. And we'll talk about your, I'll look at your quiz, and I'll look to see where you have problems, and we'll talk about that in the next class. Are there any questions that you guys have? Anybody have any questions? So what I need you to do is read. Read chapter 2. Now you can begin your coloring book. If you look under the content section down at the bottom, you'll see your first set of colorings. If you haven't already done them, go ahead and start your coloring, because it's really now that you can begin the coloring as we talk about gross anatomy. Okay? And so we're talking about structure and function in the next class and trying to move on into internal anatomy. It won't be long. Anybody have any questions? Any questions, guys? If you don't have any, please say no. Okay. All right, so go back and review the lecture tonight. Please go back and look at your structures, look at your PowerPoints, learn them. Now, I would love to continue class tomorrow, but if I did, could you guys come back for 1 hour? Like from 6:30 to 7:30? It would help me get you through gross anatomy. Okay. Well, then I'll wait. It doesn't matter to me because we can, you know, we're going to go 4 hours on next Wednesday. Okay. Now, it's better if I'm in front of you, so if you have questions, then you can answer those. I can answer those questions. But what I will tell you is to go ahead and read Chapter 2 and learn the structures in Chapter 2, because you will be responsible for them. And I will go through them, so don't wait on me in a lecture. You are responsible for reading Chapter 2. Go ahead and look at your PowerPoint so that when we come back, if you have questions or if you don't understand content, I can answer your questions, okay? Yeah, we are, because you'll be here next week. So you come on July the 5th, I believe, and so that's Wednesday, and I have a classroom available Wednesday night. Okay? And you'll have class, everybody, is there anybody that's not coming to class? No, the class will be from 5:30 to 9:30. It can be earlier if you guys finish earlier, but I don't think you're going to be out of clinic until 5. We can do our class next week earlier, though. Absolutely. Okay. But what will happen is when you get into your sites, you're not going to be finished, I don't think, in time. So, yes, we can go to class at 5 if you guys are available then. Okay? All righty. Okay, so that being said, then now we'll see you next week, and we'll call it a night, okay? And thank you so much. I do apologize again for not being able to get to class earlier. All right, good night, guys.